Moving on. So in this chapter, chapter 5, we're going to be doing factoring, which is the opposite of distribution. We're going to learn some different factoring techniques for different forms of polynomials, and that's kind of the way it's going to go. There's a couple different ways of factoring, and then there's a few different average forms of polynomial that we factor. And so we'll go over some different cases. We're going to learn how to use those as a tool for solving polynomials, and then we're going to actually do that. We're going to solve them. So that's in the chapter, though. This is more just in the section here. So in this section, we're going to be going over factoring polynomials. Now in this 5.1, we're just talking about factoring something out of each term in a polynomial, right? The next chapter, we're going to be talking about factoring the entire polynomial. And so, what I mean by that is, in this chapter, we're going to be saying, 3x squared plus 3x plus 3. And we're going to factor each term of this polynomial and pull a 3 out to have 3 times x squared plus x plus 1. But in the next chapter, we're going to be doing we're going to ask you to factor everything, including what's in here. And so we're going to learn how to factor this guy too when there's no common terms to it. But in this chapter, we'll just learn this very first operation where we're factoring a single factor out of all the terms. So what does it mean to factor? So to factor a polynomial is to find an equivalent expression that is a product. An equivalent expression of this type is called a factorization of the polynomial. So keep in mind, it gets a little confusing because we use factor for two different things now. You can factor a polynomial, but then again, a polynomial has factors. And so it's an element and it's an operation. So keep in mind that those two can get a little bit confusing. And then of course the final, after you've found all the factors, then it's called a factorization. All right, so let's start out with monomials. And remember, a monomial is just a single-termed polynomial. So to factor a monomial, all we do is we write equivalent monomial. That should say monomial. Equivalent monomials with equivalent products. So what I mean by that is, for example, if somebody asks you to find 3 different factorizations of 15x cubed, you just split that up into its factors and you arrange them in different ways. That's all that means. And so right here in line A, you can see we split 15 up into 5 times 3 and x cubed up into x times x squared. Well, we just rearrange those factors and we can come up with 5x times 3x squared. That's one factorization. Another way we could do it is, again, split up the 5 and the 3. We can split up the x squared and the x, and we can attach the x squared to the 5 this time instead of to the 3. Right? We're just rearranging factors, that's all. And there's more than 3 factorizations of this. This last one, we split up the positive 15 into factorization of negative 5 and negative 3. And then we just went ahead and left the x cubed as it was, and we rewrote it in this arrangement of factors. Does that make sense to everybody? Right? And so, factors, split them up, rewrite them. That's kind of how you do it. All right. Okay. And sort of one of the biggest benefits of this is you might have a polynomial that's made up of 5 or 6 monomials like this, and it helps to figure out if there's any common factors to find different factorizations of the monomial and see if it matches factors in the other terms. We'll go over that in examples here. So we're about to factor some polynomials instead here, and that means we're factoring a single term out of a bunch of monomials. So to kind of jog our memory on this, let's just go over distribution real quick, which again, factoring is the opposite of distribution. So if I asked you to distribute this 3 into this polynomial, we would multiply each and every term by 3. That would give us 3x plus 3 times 2x plus 3z. And in the end, when we simplify everything, our polynomial is this guy. Now suppose we're asked to do the opposite of that, and we're asked to factor this polynomial that we ended up with up here? Well, we already know that we can factor a 3 out because that's what we distributed in the beginning, right? And so we're going to rewrite this polynomial, right? We're going to rewrite it. And watch that I just go backwards in the steps, right? And so now that we're going backwards, this is step 1. This is step 1. So for step 2, I'm going to rewrite it in its factored form. So this is 3x plus 3 times 2x plus, whoops, that shouldn't be an x, that should be a y. Sorry, this x should be a y right here. Otherwise, we can just add those. All right, so 3 times 2y plus 3z. And then we notice that they all have a common factor of 3. So that means we can pull that guy out and factor it out. So now we go to step 3 here, which is sort of the beginning step up here with our distribution. So now we pull the 3 out. And we just write whatever we have left here after we pull that one factor out. And so we had an x plus a 2y plus a z. And that's it. Like, you know, when somebody asks you to factor a polynomial, and, you know, we're in the cases where we're only factoring out a single factor, you know, just think of it as the reverse of distribution. All right, so let's do an example here. So suppose somebody wanted us to factor this guy, 8a minus 12. Well, step 1, or well, this is sort of like step 1, right? Take a look at it, write it in its factored form. So this is, let's see now, 8 splits up into 2 times, I guess we can factor out a 4. So hold on for a second. So, okay, so 8 splits up into 4 times 2, a, and then 12 splits up into 4 times 3. So you'll notice that I could have split the 4 up further, but I don't really need to because I see it's contained in both terms. So like the 4 just comes out. If I split it up further, it would be 2 times 2, and then we'd pull that same thing out, 2 times 2. But it doesn't, you know, it doesn't really need to be that way. All right, so we notice that we have a common factor of 4. We're going to go ahead and pull that guy out. So we have 4 on the outside times what we had left on the inside, which is 2a minus 3. All right, if I wanted to do that without skipping the step where I just, you know, sort of called 2 times 2, 4, I'd write it out in its fully factored form. So this is sort of the long way to do what we just did. Right, and so I still have the common factors of 2 times 2, and so I could pull them both out, which would give me 2 times 2 on the outside. And once again, it would still leave the 2a minus the 3 on the inside. And then we'd just multiply the 2's out. And so, yeah, you can go all the way down to its prime factors, or if you recognize that like both these factors are just contained in each term, you can do that too. Either way is correct.
So the answer for factoring, that one is top one or bottom one?
Both. Yeah, so the bottom one, you'd have to take it this one last step, and it's the same, right? 2a minus 3. Yeah, in the end, like, you know, you can do the factorizations different ways, but you should come up with the same answer, right? If you're coming up with different answers, there's a problem.
Do we factor until we can't factor?
Yes, good question, good question. Yeah, don't factor the first factor you find, factor all the common factors are out, right? If you can factor a 2 plus a 10 out, don't just factor one of them, factor them both, factor the whole 20. All right, so this guy here. So, first of all, let's go ahead and write this in factored forms. Does anybody see a common factor with these two, 24 and 30?
6.
6. Nice, right? So 24 splits up into 6 times 4, right? So I'm going to write our common factor in red. So we have 6 times 4 times x to the 5th plus 6 times 5 x squared. All right, so I wonder if I should do this step at a time or all at once. I'm just going to do it step at a time. So we'll notice that we have the two factors of 6. Some of you might see that we can factor something else out right away, but we're just going to do this baby steps until I start skipping steps later on when you guys are comfortable. So I pull these two 6's out, which means I write a 6, and then I put my parentheses in, and then I just finish the problem, like finish what's left in here after I got rid of the 6's. So I'm left with 4x to the 5th plus 5x squared. Now I'm going to notice that I have other common factors, and those are my variable factors. So I have 2 factors of x in this final term and 5 factors of x in the first term. How many factors of x should I factor out? 2, right? And that's because, like, if you picture this, if you picture what all this is in longhand, right, this is 4 times x times x times x times x times x plus 5 times x times x. And we say, hey, look at that. We have at least 2 common factors in each, so we can pull those out. All right? So you should, and after a while, it'll take a while before you get too comfortable with this, but after a while, you'll be able to just see that right off the bat. And so on this next step, we're going to take this x squared, and we're going to pull it out of each term. And so we're going to have 6x squared, and that's going to be multiplied by, whoops, let me just write it down here. So we're going to have 6x squared multiplied by 4x to the 3rd plus 5. How's it?
Where'd you get the 6x squared?
So I pulled an x squared out of each term, right? Which means that it comes out with the 6. All right, and so I took this x squared on the 5x, and so I'll check this out. So let's see now. So if I wanted to, I could say x to the 5th. If I wanted to get rid of all the extra coefficients and stuff, x to the 5th plus x squared, and I said, well, factor something out of that. I can factor an x squared out. So I get x squared out front times x cubed plus 1. And so that's where the x squared came from. And it got attached to the 6 because I already factored the 6 out. I took it in baby steps. If you do this all at once, it probably makes a little bit more sense why those two are attached. But if you look back to this step here, I could have recognized that there were other common factors and factored it all out at once. All right. So I think we already went over this. When we ask for a polynomial to be factored, we do mean a complete factorization. So not just one term factored out, we need all possible terms to be factored out, right? If we wanted to say, well, just give me one factorization of this initial polynomial, we could have stopped here. But it wanted us to completely factorize, so we had to go all the way to this step. All right? All right, so let's do a couple more examples, since those were probably pretty confusing anyway. All right, so what do we have here? Do these have a common factor? 12, 15, and 27. Let's take a look. Let's do this let's go all the way back to our factor trees and find out. So 12 is 3 times 4, which splits up into 3 times 2 times 2. 15, well, that splits up into 5 and 3. Those are both prime, so we stop. 27, that splits up into, 9 and 3? Yeah. 9 and 3, which actually splits up into 3 times 3 times 3. Okay, so we'll notice real quick, these guys, just like you guys said, they all have at least 3 in common. But there are no other common factors, so that's all we can pull out as far as the coefficients go. Huh?
Does that stay out front?
Yeah, and so the 3, when we get done, the 3 will be out in front of the parentheses. Now the other thing we're going to do, we're not going to take this in baby steps. We're going to really quick notice all of our variable factors too. And so we're going to factor this one all at once. So notice that we have 3 terms here. We have 5 variable factors in the first, 4 in the second, and 3 in the third. And so we have 3 common variable factors to each. We can't pull out 5 because one of them doesn't have 5, right? We can't pull out 4 because one of them doesn't have 4. We can pull out 3 because all of them have at least 3. So let's go ahead and rewrite this guy. I'll write it down here in our factored form. And I'll write everything we're about to pull out in red. So this 12x to the 5th, a factorized version of this is 3 times x cubed times 4x squared. Does that make sense? I just rewrote 12x to the 5th as this guy, except for I wrote what I'm going to factor out in red so I can remember that's what's happening. The next one, I'm going to do the same thing. So I'm going to take out, once again, that common factor of 3x cubed. So I'm going to rewrite this second term as negative 3x cubed times 5x. Now with our last term, this plus 27x cubed. I'm going to write that as 3 times x squared, or x cubed, excuse me, times 9, exactly. All right, so now I've rewritten this polynomial with the factor that I want to take out. I'm going to go ahead and take it out on this next step. 3, oops, wrong color. 3x cubed is what I took out of each and every one of those guys. And now I'm just going to go up and see what I have left. What I have left is everything I'm highlighting in yellow up here, everything that was blue when I did my last operation. So I just write those down inside the parentheses and I'm done. 4x squared. It's now a quick little detail here. I almost screwed it up. Yeah, it's still a minus, right? Because we factored out a positive 3x to the third.
5x?
Yeah, so it's minus 5x. Be careful with that one. That one will get you. It almost got me right there. All right, and then we have the plus 9 in the end. Okay, so that is, at least at this point, the fully factored version of that. In the next chapter, we're going to learn, actually it'll be 5.3 before we learn how to factor guys like this, but eventually we're going to be factoring these inner polynomials as well. But this is just the beginning. All right, so this guy here. So it looks like we have 8 and 16 there. We got a common factor of 8, right? So what else do we have common factors of? So now we have 2 variable.
4.
Let's see now. So how about for R? How many? Just 1? Good, right? Because each one of these has at least 1 R, but not every one of them have more than 1 R. So we're going to rewrite this guy. Let's see now. Why don't we just start by, so I can keep track of this, I'm just going to write what I'm going to factor out up here. So we know we're going to factor out an 8. We know we're going to get 1 R and 1 R only. How many S's can we factor out? 2, right? Because each term contains 2 S's, but one of the term contains no more than 2 S's. And so that's really all we can factor out. So S squared. All right, so I'm going to rewrite this first term in its factored form. And so this is 8R S squared times what's left, which is R to the 4th, and not S squared because we already took that guy out. So now we're going to write this next one. We're going to factor out the 8R times S squared. And that's going to be multiplied by 2 2s to the third. All right. So I've written everything in its factored form. If I want to check my work real quick, I can look back and make sure that all this stuff actually multiplies out to our original polynomial. The next step is going to be to pull our selected factors out. So we simply write out our factor, 8r s squared, and then we put in our parentheses, and we fill in the parentheses by whatever we had left up here, which is r to the fourth plus 2s cubed. All right. Any questions on that one? Okay. Good. Okay. How about this weirdo? Let's see now. So we have threes and sixes for our coefficients. So I'm going to go ahead and start up here by writing what I know I can factor out of this, right? So I know I can at least factor a 3 out of this mess. It appears as though there's a negative on each and every term, so although we don't necessarily have to do this, we're going to do it anyway, just because it's better. So we're going to factor out a -1 from each term as well. Now, let's note real quick that each term contains an x, which means we can factor that out as well. However, when we look at these last variables, we have a y in one term, a z in the other term, but those are not contained in the other terms, right? So we cannot factor those out. So our common factor is going to be this guy, -3x. So let's go to the next step and start writing that guy out. All right, so we're going to rewrite -3x out of each of these factors. So -3x times what's left, which is y. And then we have a -3x times what's left, which is 2z. And then I have -3x, period. And just as a little reminder to myself, so I don't forget this, I'm going to put times 1 over here. All right, next step. We take everything that we've determined as a common factor and we write it out in front of our parentheses. -3x, write in your parentheses, and then in your parentheses, you just write out what you had left. And remember, we factored out the entire -3x, and so the sign on all these terms will change. And so what's left is y plus 2z plus 1. All right. So, tips for factoring. If you guys want to check this out, it's on page 307. So, yeah, it's basically, we just go over what we just did. So you factor out the largest common factor if it exists, and then if you want to check your work, you can evaluate your initial polynomial with your end polynomial and make sure you get the same answer, and so you'll plug in like 1 for x in your initial and your ending polynomial, and if you don't have the same answer, you got a problem. All right, factoring by grouping. This method is a little strange, but it makes sense if you repeat it enough times. So remember, before we found out the FOIL method, we went over sort of how to distribute your way out of this multiplication. And it involved distributing this entire binomial over here on the left side, this x plus 3, into this binomial. And so we said x plus 3 times the first term, which was x squared, and x plus 3 times the second term, which is 4, -4, excuse me. Then we would do our distributions on each of these connections. We distribute our x squared in and our 4 in to get this next line here. And then we'd write out our polynomial. We'd do the multiplication, right? And so what we're about to do with these factor by grouping, we're reversing this operation. Just like the other one, we were reversing a different distribution operation. With this one, we're reversing the distribution operation that comes with this weird multiplication technique. So what we usually do with the distribution technique is we arrange 4 different terms, and having 4 terms is a pretty good indicator that you're about to use the grouping technique. I mean, it's just the way math books work. So what we do is we consider this one full polynomial and then this one full polynomial. We factor out common terms in each, and then we go ahead and factor out binomials. That sounds confusing, so let's go ahead and do the operations. Okay, so in this first one, I see that I have a common term of x squared. So I'm going to factor out x squared from both of those first 2 terms. That's going to leave me with an x and a plus 3. Okay, so now on these second 2 terms, I'm going to notice that I have a common factor of a 4. So I'm going to go ahead and factor a 4 out of those. And I'm actually going to factor out a negative 4. And this is maybe, if there's a negative sign in the middle, it might be better to do your grouping kind of like this. Make sure you put a plus sign in here so you know it's not multiplication. Yeah, it's just a little weird to write it like that. So I'm going to pull a negative 4 out of both of these terms. Okay, so when I do that, I have negative 4 out front, just like usual. And then what do I have left on x plus 3? Does that factor make sense to everybody? Okay. What's that? Oh, whoops. Cha-ching, squared. Thank you. Okay, so now here's the part that's a little bit weird. So remember up here, right? And so this step that we're on now matches this step that we did in the example, right? These are kind of the same, where we have this x squared and this negative 4 hanging out outside of 2 binomials. We have kind of the same thing right here. Okay, so the next step, what we do is we pull out our common factor from both of these terms. Our common factor is the binomial in parentheses x plus 3. So we say x plus 3 outside, and then we write what we had left, which was x squared and negative 4. And so that's it. The transition between these 2 steps is often like, it's weird, I know. Don't feel bad if you're like, wow, that's kind of strange. But yeah, that's just the way you do it. And once again, if you're nervous you did this wrong, evaluate this initial polynomial by, say, plus 1, and then evaluate this ending polynomial by the same plus 1 and see if it works. All right. So that was, let's do another one of these guys. So suppose we're at this stage. We're already at a decent stage, right? You know, this is sort of the middle stage of the whole factor by grouping thing. And so if you see something like this, all we need to do is notice that these terms, this first term and the second term, have a common factor, and that factor is the binomial in parentheses x plus 1. So I'm going to pull the x plus 1 out of each term. And I have x plus 1 times what was left, which is x squared plus 2. All right. So, is this the last one? Yeah. So, once again, we're asked to factor something. You know, we notice that there's 4 terms. That's like a dead giveaway in this class that it's probably going to be easier to factor this by grouping. So we consider the first 2 terms and we say, do they have any common factors? And then we'll consider the second 2 terms and say the same thing. So on this first guy, we have 5x cubed and negative x squared. There's no coefficient on the second term, which means we can't really factor out a number, but we can factor out an x squared. Each term contains an x squared. So we say x squared on the outside, and then we write what we have left, 5 with a single x minus 1. With this second guy, my common term looks like it's going to be 3. There aren't any variable factors, so there's no common variable factor terms. So I'm gonna pop a positive 3 out. So I have plus 3. And then I rewrite this guy. 15 divided by 3 is 5x. 3 divided by 3 is 1. Okay, so now here I am. I have this common term, 5x minus 1 in parentheses, so I'm going to pull that common term out. So this guy is going to equal 5x minus 1 times x squared plus 3. And there we are. All right. And I've said this before, but if you run into a factoring problem and you're not exactly sure what to do, but it's got 4 terms, just try factor by grouping. It's pretty easy to do. It doesn't take too long. It's just a worthwhile try if you're not sure what to do next. All right. So how about I turn you guys loose on this guy here? Go ahead and get a piece of paper out and see if you can figure that guy out. Feel free to talk to your friends and neighbors about it. Make sure you got the right answer. All right. What's a common factor I can get out of these first 2 terms? 2? What else? X squared. Cool. What about this one? Do I need to factor anything out of this second? Yeah, there's nothing to factor out, and it can stay the same anyway because it's going to work fine. So after I divide this term by 2x squared, I would have a single x. After I divide 8x squared by 2x squared, I would have a plus 4. So we have, let me actually rewrite this in different colors here. All right, and so this other binomial just stays the same. And so this is 1 times x plus 4. So I notice that I have a common term, or a common factor in each term, and that is the binomial x plus 4. So I'm going to go ahead and factor that guy out. So we're going to have x plus 4 multiplied by 2x squared plus 1. And keep in mind, it doesn't really matter which order you write this in. So this one, once again, is, it's the same thing if you swap these guys around. You could write it 2x squared plus 1 times x plus 4 if you wanted to. Doesn't matter. Oh, let's see now. So for this guy, if I miss a term, either missed a term or we have to just rewrite this one real quick. Oh yeah, I missed a term. This should have a minus 3t there. Okay, so for this guy, once again, we would just separate our two groups. And every once in a while, you might have to rearrange these guys to get them into their groups. That's not usually the case with this book. Yeah, it's really, they usually just set it up for you. But every once in a while, you will have to rearrange terms. Okay. This could be one of those cases. Take a single t out. This is one of those cases, maybe. I think you are correct. Yeah. Yeah, so t plus 5 is what we were looking for. Okay. So we can rewrite this guy as, let's see now. So you were saying, what was you're saying 4t cubed minus 3t, and then do this other thing as plus 20t squared minus 15. Does that make sense? It's 3t.
Wouldn't you want to do the 4t cubed?
Yeah.
20t cubed preserved?
Yeah, you're right, Juan. There you go. Yeah, I got all those all wrong. All right. Here we go. So minus 3t goes out here, and then minus 15 goes in here, right? Did I do that wrong again? No. It's the same, huh? Sorry, guys. It is one of those days, isn't it? All right, negative 3t and minus 15. Okay. Hey, look at that. We might actually have it there.
I think you wrote it wrong again.
Misty? All right, so let's go ahead and get this over with. All right, so on this first one, it looks like we can factor a t out. So we're going to do that, and we have 4t squared minus 3 plus, what can we factor out here? We could factor a 5 out. So we have 5 times t squared minus 3. 4t squared. All right, so we have the common factor of this guy, 4t squared minus 3, so that's what we can factor out. We're going to go ahead and do that. So we have 4t squared minus 3 times t plus 5. There we go. All right, Sometimes you're going to want to factor out a -1 in order to get your terms to match. So, for example, with this guy, if we factor out a t to the 4th on this first set, then we have t minus 5. And then if we factor out, if we were to factor out a positive 2 on this next set, we would have 5 minus t. But we'll notice real quick that these guys don't quite match. They're just opposites of each other. So we can factor out a negative out of this last one to make them match. So I can rewrite all this as t to the 4th times t minus 5 minus 2 times t minus 5. Now they match. Now they're good. And so you can factor out that negative, that extra negative, if it helps you out. So now we can rewrite this guy, pull out our common factor and rewrite it as t minus 5 times t to the 4th minus 2. All right. And once again, we just factored this guy, but this guy could be factored further, which is what we're going to keep learning in this chapter. Checking your work, once again, for this last one, if we wanted to check our work, we could evaluate this initial polynomial for t equals 1, then evaluate this ending polynomial for t equals 1 and see if they come up with the same answer. If they're not, that's no good. If they do, it's likely they're the same, but not guaranteed. If you want a guaranteed, you might want to check one more point. And even then, it might not be guaranteed. All right. So this will probably be a little bit of a quick class, but we were only supposed to do chapter 5.1 today, but we're going to do an introduction to factoring we're going to do an introduction to factoring trinomials. And then by tomorrow's class, it won't be the first time you've seen it. So if you come up with any good questions in tonight's homework, please write them down and ask them for tomorrow's class. So, you guys see okay? Do I need to turn the lights on or anything? Everybody's good? Okay, so I wrote the common form that we're going to be dealing with right up here. X squared plus bx plus c. Throughout this chapter, I'm going to be talking about b and c. Those are the two crucial values in this general form. Like, examples of this general form are stuff like, I'll do that one here. Examples of things that conform to the general form would be like this first example, x squared plus 3x plus 1, right? It definitely follows the form of this type of polynomial, where b is equal to 3 in this particular example, and c is equal to, whoops, it's not -1, it's +1. +1. Right, and so when I say this general form, all I mean is that it looks like this, right? Something that to note is that there's a 1 in front of this x squared. There's no coefficient on the leading term. When there's a coefficient on the leading term, things get a little different. That's what we'll be learning in next chapter. So here's another example. The polynomial x squared plus 5x minus 2. This is good. We're in the right form. b equals 5 in this example, and c equals a -2 in this example. All right, here's another one that follows the form, x squared minus 16. This one, though, b equals 0. It's still valid. These numbers b and c can take on any real values. And so since b was equal to 0 in that example, another example that works is like something like this, x squared minus 5x. And then with no constant. In that example, the c is equal to 0. Here's another one. This guy. This guy does not fit the form that we're working with in this chapter because it has a 5 up front here. That's not allowed. Our form says we have to have a 1 up there, so it doesn't match. All right? We're going to be dealing with these in next chapter, not this chapter. All right. So, one thing that we should note is, like, when we have these forms, when there's no leading coefficient, these are like what I might be referring to as the easy cases. That doesn't mean they're easy, so don't think that I'm trying to degrade them or anything like that. I just mean they're easy relative to the next stuff we're going to be doing. So don't think that I just think you guys should just get this immediately. They're just easy relative to other things.
Yeah.
All right, so quick note, I know I've already mentioned this. If you guys want to do good on the next exam and on all other algebra exams after that, factoring all trinomials is going to be crucial. So 5.2 and 5.3 is going to be very crucial. All right, let's go ahead to the concept of this whole thing. So we're going to do some exercises just to kind of outline what's happening here. One thing that we note while we're doing all these exercises, and these exercises we're going to be foiling out binomials, right? This is the operation we're about to learn how to reverse. Let's just notice that the product of two binomials is a trinomial. The coefficient of x in the trinomial is the sum of the constant terms of the binomials. And finally, the constant term in the trinomial is the product of the constant terms in the binomials. This is going to be easier when I show you by example. But I have to say it out, okay, just in case. I got to be rigorous here. So, okay, what all that is really saying is that, what it's saying is that when you notice the O and the I terms, right, see right here, my O and my I terms are 3x and 2x. When I add those up, it's going to be 5x. 5 is the sum of these two numbers. That's one of the patterns that you need to notice. The other pattern is that your L is the product of these two numbers. That's really the other pattern that you're going to want to notice. If you have those locked down, it's not going to be too hard doing this. So, okay, let's go ahead and see how that works here. So suppose I was doing my FOIL, right? My F is my first terms. My O, that's going to be x times -5, so -5x. My I term, my inner term, is going to be -2x. And then my last term is going to be -2 times -5, which is going to be a positive 10. All right, so when I combine all that, we have x squared minus 7x, and then plus 10. Now let's notice real quick, this -7x, that is -5 minus 2. So when I add these two terms together, I would get the coefficient of this term. When I multiplied these two terms together, I get this final term. Okay. Let's do another one real quick. So, if I FOIL this guy out, my F is x squared, just like always. My O, my outer terms, is going to be -7x. My inner term will be a positive 3x. And then my last term is going to be -21. Okay, once again, when we combine all these, I get x squared minus 4x minus 21. Notice one more time, this -4 is what we would get if we took a -7 and added 3 to it, right? That's the combination of these two numbers. That's the sum. This number, -21, that's what we get when we multiply those two numbers. All right. So, also notice, this is interesting. In this example, things are getting a little messy up here. I'm going to try and make this clear. In this example here, we had two negative terms, a -2 and a -5. That meant that this last term was a positive. In this example, we had a +3 and a -7. That meant that this last term had to be negative, right? And so it's the combination of those two that determines the sign of this last term. All right, let's do one more. And let's notice real quick Oops. Actually, that's the same. That's the same one. I don't know why that's on here. Cha-ching. All right. So that's kind of the pattern that I want to point out before we go into this. All right. Now let's talk about cases. So when we are factoring out our general form, x squared plus bx plus c, we're going to look at our general form and we're going to say my factorization is going to look a certain way depending on what the sign of c is and what the sign of b is. And so we're going to go through cases for each of those examples. So let's see now. What are the cases? So the two cases, we have two cases and then we have sub-cases for each of those. And maybe I'll make a tree for you guys tomorrow to get this all correct. So case 1 would be the constant term is positive. Notice this is a positive 3, right? So that means that my factorization of this, right, this splits up into two subcases, right? So my factorization is either going to look like this, x plus something and x plus something, or it's going to look like this, x minus something and x minus something. Does that make sense at all? Because this is positive, the only two options are a positive times a positive and a negative times a negative, because this last term is the product of these two terms. All right? So for this one, for the next case, is when the constant term is negative. That guy breaks up into two subcases as well. The subcases for that, well, at least in this example, it won't have two subcases. But the subcases are, at least the first one, is a positive and a negative. That's the only way that you can multiply two numbers together to get a negative, is if you have a positive and a negative. And there is a second case down here, but it's just determined by the value of b, and we'll get into that in a minute. Okay, so unless a trinomial like this is prime, it will always split up into a factorization looking something like this: x plus p times x plus q, where p and q are dependent on the values of b and c from our general form. So what we're talking about, a p and q, right? So we say this is basically what we're looking for. To complete this problem, all we need to do is find p and q. So we look for a p and q that work for this particular combination of positive 6 and positive 9. So yeah, let's go ahead and do this one real quick, right? And so what two factors multiply to 9 and add to 6? 3. Yeah, so this one is x plus 3 times x plus 3. It's okay if this is confusing. It's totally fine. You're supposed to be confused. That's why we're going to do this whole thing over tomorrow. All right? So let's go ahead and start doing some examples with these and try and identify our own pattern. So everybody go ahead and get out a piece of paper and write your name at the top. And this won't be graded, but I do just want to take a look and see how everybody's progressing in class with this stuff. All right, so for these problems I'm about to give you, you'll want to first take a look at the problem and guess what you think the sign of B and C will be. Next, in part B, I want you to multiply each pair out and identify the actual sign of B and C. Check your initial guess. So I'll do this one in front of you guys so you'll know what to do. So I'm going to look at this guy and I'm going to say, well, I have a 2 and a 5, right? This has got to equal x squared plus bx plus c, right? I know that c is the product of the second terms in the binomial. So I'm going to say, I don't know, for part A, I'm going to say guess C equals 10. Now, the other thing we notice is that these two terms, our constant terms in our binomials, they must add to B. So I'm going to also guess that B is equal to 7, because that's what 2 plus 5 is. Then I'm going to do my multiplication and go ahead and confirm. So part B, I'm going to go ahead and multiply this guy out, and it equals x squared plus 5x plus 2x plus 10, which in the end is equal to x squared plus 7x plus 10. So I can see that, yeah, I did the right guess. And I guessed right. It wasn't really a guess. I just followed the formula. I followed the rules that I knew had to be true. Okay? So, starting with number 2, go ahead and do part A and part B for each. So remember, part A, we're guessing for B and C, and then part B, we're actually doing the multiplication.
So A is to guess what B and C equal?
Yeah. And you guys can talk to your neighbors if you want to. It's okay. It's not graded or anything. It's totally fine to ask your neighbor what the heck's going on.
Goes to all three?
Yeah.
Just out.
Uh-oh. How's everybody doing? Almost there? Not almost there. All right, go ahead and write them down and finish them after the lecture if you're not done yet, just because my battery's running out. Otherwise, I'd give you guys more time, but I think my computer is going to die before the lecture's over, so. Yeah, right? Like, why didn't it run out half an hour ago? Yeah, so for this first one, I'll just do this first one real quick. So for this first one, we know that B has got to equal what? -5, because that's what -3 minus 2 is. And we know that C has to equal what? +6, because that's what -3 times -2 is. All right. And then you just multiply them out to confirm. And if you do it that way, they're all correct. All right, so let's talk about the cases real quick. So, for our general example again, we have some P and some Q that this actually works for. If we have this polynomial, this is how we'd kind of evaluate that. We'd say, okay, the last term is a +25, and so we're looking for P and Q such that P times Q equals 25. That's one condition, right? These are good conditions to write down. So then the second thing we're going to look at, we're going to look at this number 10. Oops, that's incorrect. This should be 10x. I'm sorry. That doesn't make any sense. So this should be an x. So we look at the middle term, 10x. And this tells us that P and Q must combine to equal the coefficient of that middle term. So that's the second rule, or the second condition. So all we need to do is say, well, let's think of factors that combine to equal 25, and let's think of two sums that combine to equal 10. To do this, we can just fill out a factor table. And so this is kind of how I like to do this thing. So I fill out this table like I have over on the right. I guess I should say this first. So there's a couple different ways to do this. One way is to fill out a table like I'm going to show you here. Another one is guess and check. That's fine too. If you practice enough, you will get what is called factor vision. I trademarked that. This just means that you're going to see it, you're not going to need to do that intermediate step after a while. You're just going to be like, oh, I get it. Like, I've done this enough times to where I can do the table in my head real quick.
It's like walking.
Yeah. So the way you do the table is you set up on one side and you write down pair factors of of your constant term, C. And then over here, you write down the sum of those factors, and you put in a little parentheses or a circle, you write what sum you want. So for this particular example, we want, this should have an X by it again, we want them to sum to 10, and we want their product to be 25. So pair factors of 25. Well, there's 1 and 25, and then there's also 5 and 5. Well, but then there's also -5 and -5, and then there's like -1 and 25. Oh no, that doesn't work. -1 and